Thank you, Fred. Ladies and gentlemen, thank you for enduring with me this little what is turning out to be a little series of webinars on reliability analysis. Now what? We're up to webinar number 2 of what's going to turn into a number of webinars moving forward, because this has got such a really good response to the very first one when we explain what we're trying to do, which is actually take data, failure data, and turn it into really useful decision actionable information, which is a fancy way of saying we created something that you can make a decision on. A lot of the time, reliability engineers or people who do reliability stuff get caught in the trap of using software and getting limited to the capabilities of commercial software and saying, well, if that's all the software can do, the answer needs to be somewhere in there. And obviously 9 times out of 10 it's not, and we're left feeling confused. And decision makers in particular look at us as reliability engineers in a quizzical way and say, thank you very much for your time. I don't even know what a Y-ball plot is. We're going to launch a product today regardless. So it comes down to working out what we want to do in terms of informing a decision and then going from there. So I can see we've got a few people joining. I dare say a few more people will turn up. I highly recommend for those of you who are joining us today who haven't seen the first webinar, in the fullness of time, make sure you go back and check that out. We're going to do a quick review of what we covered last month when it comes to reliability analysis and in particular what the Markov chain Monte Carlo simulation did for us. But this is supposed to build on what we did last month. So last month when we looked at reliability analysis, now what, number 1, we looked at a very typical scenario where we are investigating the time to failure of a product, system, service, or thing. And so if this arrow represents the axis along which we represent the time to failure of our thing, we become really interested in the data points that fall along this line. And as we all know, failure is a random process. So frustratingly, we have things like material imperfections, variation in manufacturing, we have seasonal weather changes, and last but certainly not least, in fact, this is the most important influencing factor most of the time, we have different ways our customers and users use the thing we're creating. And all these different sources of variation, and there's tons more than these ones, and combine to create, let's call it our random hand of failure. And this hand is supposed to characterize or summarize all these uncertainties as they come into play and influence how long it takes before our thing fails. So last week we looked at some data, but the data was actually a lot closer to 0 than this hand suggests. So I'll move our hand over here. And the data we looked at is coming on the screen right now. So we created this, we did some tests, we've got some field data, we've got all these data points, all these different times to failure for our product, our system, our service, our thing, whatever it is. And then we plot this data on what we call a Y-ball probability plot. Now, where the vertical axis is the probability of failure, or perhaps the expected fraction of things that have failed. So these weird axes, you can see that on the horizontal axis, there is a logarithmic scale. On the vertical axis, there is a really weird scale of percentage of things that have failed. This is because this particular set of axes is what we call Y-ball probability plotting paper. A bunch of really smart guys and girls have worked out that if we skew our axes scales in this particular way and data gets plotted on these axes, if we see a straight line, we can be reasonably comfortable that the underlying process describing our failure, our random hand of failure, is the Y-ball distribution. Now, we're not going to go into the Y-ball distribution in great detail today because we have another webinar on probability distribution functions and things like that, which again, if you need to brush up on what those things are, then feel free to go onto accendoreliability.com and check out that webinar if you need to get on top of this thing called the Y-ball distribution. The reason we love the Y-ball distribution is because it can model things that wear in, so they have a decreasing failure rate or hazard rate, typically due to manufacturing defects. It can also model things that have a constant hazard rate, which is quite rare, but does model things that are failures that are caused by external stresses like car crashes or lightning strikes, things where these randomly occurring external stresses come along. When they do come along, they are catastrophic. They destroy your thing completely. There's no accumulation of damage. When you have that voltage spike for that PCB, it explodes or short circuits. Right, sorry, it won't short circuit. It will perhaps arc or otherwise destroy itself when that rogue voltage spike comes along. So it's a constant hazard rate. And last but not least, reliable distribution is really good also at modeling things that wear out, where we're not having those single catastrophic spikes of stresses. Where what we're talking about there, sorry, is where our thing accumulates damage with respect to usage. And as it accumulates damage, as the crack gets bigger, as it gets more and more brittle, as creep tends to deform our metallic structure, or whatever it is, whatever mechanism it is where we accumulate damage, our product, our thing, our system, our service will eventually become too weak to defeat even normal or low range stresses, and it will quickly fail. So last week, when we're looking at this data, we're actually looking at the problem from the perspective of trying to set out a warranty period. So let's just say this is failure data on this Weibull probability plot for a wireless modem router, an electronic consumer product. And what we want to know is we want to know how long our warranty period can be. And now we know that historically our competitors and our previous models, they have a 2-year warranty period. And you can see that the 2-year warranty period is marked as shown on that horizontal axis in that logarithmic scale. Now, if we look at the line of best fit, when we work out where that line of best fit crosses our, look where our 2-year period crosses our line of best fit, and we project across the vertical axis, we will quickly see that this line of best fit suggests about 8% of our wireless modem routers will fail by 2 years. Now, is that good or bad? Maybe that's good. Maybe that's within the butter zone of making a profit. But the problem with this is that this is just a point estimate. Now, you can see there's a lot of data points which seem to be around this region, and none of them give me at least a great deal of confidence the line of best fit at the 2-year mark is particularly accurate. So if we want to get some understanding of the variation or the uncertainty we have in our warranty reliability given a 2-year warranty, what do we do? Well, last month we looked at solving this problem. We essentially created what I didn't call then, but I'm going to call it now, a posse of potential Weibull distributions. And each Weibull distribution has its own CDF curve, or in this case, CDF line. So we created this posse of Weibull distributions, but they're not just a random collection of Weibull distributions. We'll come to what that means later on. You can see that these lines seem to line up with our data. They seem to follow the trend that our data suggests. This posse becomes, in a way, representative of our uncertainty of what's going on. And if we have our posse of Weibull distributions, we can use each and every single one of these to work out what that particular Weibull distribution suggests warranty period failure, warranty reliability will be, or in this case, warranty failure probability. So in essence, we create a posse of reliability estimates at 2 years. Now, last week we showed that once we get this posse of reliability estimates at 2 years, or failure probabilities at 2 years, if we have enough of these data points, we can simply create a histogram of each and every single one of these. And let's take this histogram off this chart here. It's getting a little bit busy, and put it on its own chart. So going through that process of creating a posse of Weibull distributions based on the data, which creates a posse of 2-year warranty failure probabilities, we can create this lovely histogram here, which gives us an understanding of the range of possible warranty failure probabilities. But this wasn't what we're after, because if you recall what we talked about last month, we're interested in the expected profit of each unit. And we knew that the recommended retail price was in the vicinity of about $120 odd, and every time this thing failed, we had to send a new one out to the customer. So essentially, we are losing the amount of money plus cost for each replacement wireless modem router we had to send to a customer if it failed during the warranty period. And we do the math, and we can use this histogram to create an expected profit per unit. And this then, if we do this enough, we can create what is essentially another PDF curve which summarizes every single piece of information we have and relates it back to the thing that mattered to our decision maker. Will we make a profit? The answer is not quite yes or no, because there's a 40.73% chance that we'll make a loss, because based on our understanding, the failure probability could be high enough such that we will not make a profit, because we have to keep sending brand new wireless modem routers out into the field or out to our customers because we have that many failing during the warranty period. We can also work out that based on what we know right now, there's an expected 32-cent profit for each wireless modem router. Now, this is as far as we can go. We can go no further. There are no assumptions here. There is as much information we can squeeze out as possible to inform our decision maker about whether we should launch before we might, whether we should launch now, whether we should invest in making our thing more reliable, whether we should change the recommended retail price, or whether we should adjust the warranty period. Because if that person asks any of these questions, we now have the information to give that decision maker every conceivable piece of information they need to know, to make that decision. A Weibull plot by itself will not give them that information. That posse of lines plotted on a chart will not give them the information. Remember, they're not going to be a reliability engineer, you guys are. So getting it to this level is as far as we can go, and we have squeezed every little bit of information out of the data. We have turned it into decision actionable information. And yes, you might need to coach the decision maker on how to interpret this, but this is a risk-based decision-making profile. And once we've done that, we have given our decision maker all he or she can feasibly get from our data to make an informed decision. So before we go on, let's ask, are there any questions about what we covered last month for the purpose of setting the platform for the rest of this webinar? Any questions? Looks like we're pretty good so far. Hopefully all you guys did attend last month's webinar, so you know what we're talking about. Okay, all right, so that's the problem we're trying to solve. We're trying to get decision actionable information for the purpose of making informed business decisions. All right, so how do we create that posse of distributions? This is a fundamental step in trying to get this histogram. We talked about it a little bit last week, how we created a likelihood function. In fact, I'll put it in code, but that doesn't teach you how to philosophically how we create this thing called the likelihood function. How do we create this posse of Weibull distributions to answer these questions? How does one potential candidate Weibull distribution rock up and say, I want to join your posse? Well, let's go through that process in greater detail. I'm going to go through the fundamentals using illustrations, because it's so important to understand what we're trying to do before we start putting numbers and formulas down. That will happen, that needs to happen, but the very first thing you need to do is understand what those different equations represent. Okay, so this is the data we were just looking at, which created that Weibull plot, which created our understanding of the warranty period for our wireless modem router. Problem with this data for our presentation is it's really clumped together. It's not easy to see. It's got a big bunch of data points on the left. We've got one rogue one on the right. So it's difficult to see what's going on. So let's use another set of data points, which is a bit spread out. And let's just say this data points comes from a completely different system, say a pump or an axle or a transmission or a gearbox. let's look at data which looks a little bit like this. It's more spread out. We can see what's going on. So the only reason I've just changed the data was for the purpose of creating data points which are easier for you and I to see during this webinar. All right, so this is the data we're going to look at right now. We can see that there might be some tendency for these data points to gather around a central value. And this histogram is a crude way of representing how the density of occurrence of each of these, of the data points you can see on the screen. You can see it's not perfectly smooth, but you can see there's a clear tendency of our data points to sort of cluster around a central region or a central value. Now, this curve here is a probability density function curve of a particular Weibull distribution. Now, the reason I've superimposed this curve is because that curve is a way of representing the density of probability based on some model, in this case, the Weibull distribution. So you can see in this case, this PDF curve, which describes the probability density based on a selected Weibull distribution, it appears to roughly correlate with our histogram. In fact, you might look at this PDF curve, which summarizes the relative likelihood of data points falling in one region versus another, and say, you know what, visually, that looks like it's a good fit. I would not be surprised if that PDF curve described the time to failure of our pump or whatever it is we're looking at, because the data points tend to cluster around the highest, around the points where our PDF curve is the highest. But sorry, I got ahead of myself. So we might ask ourselves, is this a good fit? Now, let's compare this PDF curve to another PDF curve. You can see it's morphing to another Weibull distribution. Now, is this a better or worse fit? I'm going to ask you guys this. What's your feedback on this being a better or worse fit than that first PDF curve I showed you, which looks a lot like a bell? So it's worse. Why would that be, Mark? A couple of worses. Anyone really needs to look at the slope to answer? I disagree with that. Good answer, Mark. The data is not near the peak of this distribution, where the highest points of their PDF curve, which represent or should represent the highest density of probability, that's where you expect more of your data points to occur than regions where the data is, the PDF curve has a lower value. So, sorry, is it Striverson? If you said you need to look at the slope to answer, what was the rationale for that feedback? Why do you think you need more information than this picture to be able to conclude that this is either a better or worse fit than that bell-shaped PDF curve we looked at? Okay, so you thought it was a very easy way. Do you mind elaborating a little bit more? What was an easy way? Just a couple more seconds. Okay, so maybe we're having a couple of connectivity issues with Striverson, but hopefully you can see the point I'm trying to make. If we see a probability density function curve, the height of the curve is represents quite literally the probability density, or the density of points, data points you would expect to see if we allowed that PDF curve to govern some sort of experiment. So why is this a better fit? Because it appears as if the data points are clustered around the hot region where our PDF curve has the highest value. So you might conclude using words that this PDF curve is more likely to describe the data points we see than that other PDF curve. Now, to be clear, that other PDF curve, which didn't look like a good fit, it's still possible for this particular data to be the output of a random process based on this PDF curve, because you can see the PDF curve has some values at those data points, but it's not likely, or not nearly as likely, as this PDF curve here. So I can see that Michael has chipped in and said the one on the right will have a greater Weibull slope. So I dare say what you mean by that, Michael, correct me if I'm wrong, is that if you put this particular data set or drew a line representing that PDF on a Weibull probability plotting paper, the slope of that straight CDF line would be higher, which would indicate what we call a higher beta value, or beta parameter value, which would indicate we're out in this case, as an aside. Is that what you're talking about, Michael? Cool. All right. So yes, 100% correct. This curve, or this data point, these data points when plotted on plotting paper would give you a higher, or sorry, higher slope, which would imply a higher beta parameter, which is something we cover in our Weibull probability plotting webinar. But anyway, so if you are able to say or reason in your head that this bell-shaped PDF curve is more likely than the other one, then well done. If you haven't done this before, you are now taking perhaps your first steps in the world, or at least in the statistical world, on the path towards likelihood. Likelihood is a concept. It's technically is a probability, but we call it likelihood because it represents things like confidence we have in other probability distributions representing what we see. And so we use the term likelihood to make sure that yes, we have probability density functions over here in one conversation, and likelihoods over here when we talk about the likelihood of each of those probability density functions being true. Which brings us to the proper definition of what a PDF is. A probability density function, which we represent with a lowercase f of x, gives the relative probability that a continuous random variable is equal to a specific value. That's a probability density function. So let's go back to our data. There is a probability density function. You can see it in gray. We have this bell-shaped curve. In this case, let's just set the scene here. Let's just say we've got the data points. We don't know what's going on. This is our first foray into data analysis. All we have is perhaps a spreadsheet or a piece of paper which says our wireless modem router failed here, 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 and here. What are we trying to do? Now, I could draw this Weibull probability density function and say, you know what, this looks about right. More correctly, this candidate PDF could describe our data. How do we go about understanding how likely it is for this PDF to describe the data? I mean, it looks good, but we can't just we can't characterize how things look in a really usable way. I mean, it looks good, but how do we then turn that into something that's statistically useful? Well, what we do to create a likelihood estimate is simply look at every single data point and find the PDF value at each data point. And that's exactly what we've done here. So you can see where most of the data points occur as you would like them to at the peak of our curve, and we have some at the tails. That's great. But what we do is we find the PDF curve values at every single data point value, which is represented by these red dots at the top, and we multiply them together to get the likelihood of this PDF curve. Now I'm going to add a little scale on the right-hand side. And on the right-hand side, you see this scale coming up, which is going to represent the likelihood of all the curves we're about to look at. So in this case, the likelihood of this PDF curve, we thought it was pretty good. perhaps visually, but it's relatively low on our scale of likelihood over here. It's got some likelihood. There is some chance this describes what's going on, but it's not where we'd like it to be, perhaps, if we're trying to maximize the likelihood. So all we did to work out where this little arrow falls on this scale is multiply the PDF values at each data point. So let's look at another candidate PDF curve. Now, hopefully you can agree with me that this PDF curve here, this one which looks like maybe a skateboard ramp, a very gradual one, it doesn't look like a good fit. It looks unlikely. So how unlikely? Well, what we do is we work out that PDF curve's values at each data point. We multiply those together, and we get, in this case, a likelihood which is very low. Little arrows move way down to the bottom of the scale. In fact, it's about 2 billion times less likely than that other bell curve we just looked at, which had a slightly better likelihood. But it turns out that the most likely PDF curve, if we're looking in the world of Weibull distributions, is this one, this bell curve here. And you can see a little arrow is all the way at the top of our scale. This is the curve which has the maximum likelihood. So if we took the PDF value at each data point value, multiply them together, out of all the possible Weibull distributions in the world, this one has the highest likelihood. In this case, it's defined by two parameters. Two parameters. The beta parameter is 5.0864. So Michael, you can see that yes, we do have a relatively steep slope, which indicates wear out, and the characteristic life is, or eta, is about 1.676. So what this allows us to do is to work out that that most likely PDF curve is about 7 times more likely than that first PDF curve we looked at. In fact, I've superimposed both of them on this particular chart. Can you look at this and conclude that one of those curves is 7 times more likely than the other? The one that's more likely is the one that's a little bit shorter, a little bit fatter, and a little bit to the right. There's no way we can look at this and say, hey, that's the one. Not only is that one more likely, it's 7 times more likely. Thank you, Mark, for reaffirming that particular conclusion. But if we do the math, if we work out the PDF curve values at each data point and multiply them together, we get a number which allows us to compare in a very quantifiable way. So these curves represent, so Paul, you don't see two PDFs. Don't see those two grey superimposed in the back, it's not coming through. Can I confirm if anybody else, can somebody else see those two PDF curves? Okay, so someone else can see. No worries, Paul. With any luck, you should be able to see them in the handouts. There's a PDF attached to this, to the webinar. And if not, then worst case scenario is maybe have a look at a video later on, and hopefully those curves will come through. Okay, so this is how we can compare whether two PDF curves are more or less likely than the other. So remember that crazy term I used at the start of this webinar, the whole idea of a posse. We want a posse of Weibull distributions to help us characterize the uncertainty of what's going on. So how does a candidate probability distribution like these two join our posse? Well, we're going to give each of them a ticket. This might sound a bit crazy, but bear with me. So let's go back to our first PDF curve, which turned out to have some likelihood. You can see it illustrated on our scale on the bottom right-hand side. This is the one which is 7 times less likely than the most likely one. And we're going to give this curve a posse ticket. And the posse ticket is not just free entry. No. The green region in our posse ticket, the amount of the total ticket that is colored green, represents the probability or chance of this PDF's ticket allowing it to get into our posse. Now, our highly unlikely PDF curve, where it has barely any likelihood, well, you can't see any green in our posse ticket. So this has got practically no chance of getting into our posse. The most likely PDF curve, well, it's looking pretty good. So that the green area on this posse ticket is supposed to indicate that this PDF curve has the most chance of this ticket, allowing it to gain entry to our posse. So what we want to do is we want to make sure that each candidate PDF or probability distribution, it has a chance of joining our posse. Every curve gets a chance, but not all curves are created equal. We want the likelihood, the chance of each curve being related to the likelihood. So this curve has the highest chance of being of getting in. Our first curve is 7 times less likely to get in. Our really unlikely curve is actually several billion times less likely to get into our posse. And that's how we create our posse, or that's the underlying thing that we need to base entrance into our posse on. Then we use magic. And when I say magic, I mean Markov chain Monte Carlo simulation to essentially work out which curve gets access or not. So before we go on that, we haven't gone to Markov chain Monte Carlo simulation. We need to look at likelihood a little bit further. So just to summarize, before I have actually, I'll use this chance to ask you some questions. Are there any questions, or allow you to ask questions? Are there any questions that we've talked about so far before I move on and allow myself to get a drink? Any questions? I'll ask you guys a question while people are typing any questions they might have. Just sort of an indication, who has heard of the likelihood function before? Sean has, excellent. David has, Mark has. So I got 3 yeses. Has anyone not heard? So another Mark has heard of it, not understood it in detail. Okay. Heard of confidence bands, okay. Heard as part of maximum likelihood function or estimation, cool. Okay, so there seems to be a mixture of responses out there. We've heard of the likelihood function, and some of you, while you've heard of it, haven't really had it explained to you in great detail. So hopefully this webinar is going to fix that problem. It's because what you've been shown so far is how you calculate the likelihood if you're given a bunch of, in this case, failure points. It's quite simply the product of all the PDF curve values at those particular data points. You multiply them together and you get your likelihood for each viable distribution. So what that means is that essentially each data point has its own likelihood. So the likelihood of that particular data point is shown on the screen right now. It's that red dot. It's the height of the PDF curve evaluated at that particular point where our failure was observed for our pump or what have you. We get all the other likelihoods for each of our other data points and we multiply them together to get our likelihood. So it's just revision. But what happens if you don't know precisely when something failed? So this is all well and good if you know exactly when your thing failed. If you have all the failure points, you know exactly what time that pump ceased to work, for example. Well, let's go back to our first illustration of our problem. Got all these data points, but let's single out one of these data points, this lone data point here. So in this case, this data point you can see on the screen now represents our pump, whatever it is we're studying, failing at that particular point as measured along our time to failure arrow or axis. But this is not always the case. Sometimes you stumble across a pump, even during testing, where you don't know when it failed, but it has failed when you rock up to it. So what that means is that if you rock up to a pump that has failed and you haven't observed the actual failure event, all you know is that it failed somewhere between 0 and the time you first observed it. So if what if instead of knowing when our data, when our pump failed at a particular data point, what happens if all we know is that it failed between time 0 and time t, where time t is when we turned up? Well, that's not the only way we can introduce uncertainty. Another way is, hey, we're looking at our pump, we're testing our pump. It was we only had a certain amount of time, and our pump was still working at the end of our test period or test duration, but we had to stop the test. So we knew that if it was going to fail, it was going to fail sometime after t. So what happens if we don't know when our pump was going to fail? All we know is that it was going to fail sometime after time t, which might indicate the end of a test duration. Or maybe even worse or better, or whatever perspective you want to adopt for this scenario, what happens if you saw a pump working on Tuesday and when you came back on Thursday, it wasn't working? So all you know is that it wasn't working. When it did fail, it failed somewhere between Tuesday and Thursday. How do you incorporate this level of uncertainty into your analysis? Now, there's a ton of bad ways to do it. And in this case, the bad way is to simply take an average of these two times and use that average as an assumption that, assume that the average of these of the Tuesday and Thursday durations, then obviously the average of those two durations is Wednesday, and use Wednesday as a time to failure for your pump. That's bad. That's throwing information away and perhaps introducing bad information as well. Well, there is a really easy way of incorporating the likelihood of this data as we see it. And what we need to do is stop talking about the probability density function, that bell curve thing, and start dealing with the failure function or the cumulative distribution function, which is simply the curve which describes the percentage of things that we expect to have failed by a point in time. So every PDF curve has its own CDF curve, and every CDF curve has a PDF curve. Now, I'm not going to go into great detail about the relationship between the PDF and the CDF curve in this webinar. If it is something you need to want to look at further, we have another webinar again on probability density functions and all the functions associated with probability distributions. I urge you to check that webinar out. It's recorded on sendoreliability.com to work out what the CDF means to you. So in this case, here is a candidate Weibull distribution, but instead of representing that distribution with a bell curve or a PDF curve, we're representing it equally validly with a CDF curve. Now we have in this case a scenario where our pump was working on Tuesday, but it wasn't working on Thursday. It failed between times TL and TU. So what we now need to do is simply find where Tuesday crosses our CDF curve, find where Thursday crosses our CDF curve, and it gives us this particular value here, represented by the arrow, the distance between, or the difference between the points of intersection of our CDF curve. So just to make sure we're on the same page, just as a revision hopefully, our CDF, or our probability, or capital F of X, gives the probability that a random variable is less than or equal to a specific value. So it's a fancy way of saying that our CDF curve, our capital F of X, gives us the expected percentage of things to have failed by a particular point in time. So we go back to what we've just done. We knew our pump was working on Tuesday, it wasn't working on Thursday, and we plot Tuesday and Thursday on the horizontal axis, and where it crosses our CDF curve, we draw lines across the vertical axis. That length of that arrow is the likelihood. That tells us the probability of our thing failing between Tuesday and Thursday. So it makes it really easy to incorporate even uncertain data into the creation of our likelihood function. So we can use this data with failure data as well. It's really, really easy. So let's look at this in greater detail. If we have our CDF values at the upper and lower points of our interval, we know that the likelihood of something failing between a lower interval and the lower bound on an interval and the upper bound of an interval is simply the CDF at the later point minus CDF at the earlier point. Likewise, if we know that our thing failed sometime after t, then it's simply the CDF evaluated at infinity minus the CDF evaluated at time t. The CDF evaluated at infinity is actually 1. So this is simply the reliability function. So if your pump was still working on a Wednesday and you had to stop the test, then the likelihood of the data that you gathered, which was observing it was still working on Wednesday, is simply the reliability function evaluated at that point in time. Conversely, if we rock up on Wednesday and our pump is not working, then the probability or the likelihood of observing observing that data, where we just observed that it wasn't working on Wednesday, we didn't see when it failed, we just knew it failed somewhere between day 1 and Wednesday. We now know that the likelihood of observing that data is simply the CDF evaluated at time t minus the CDF evaluated at 0, which is 0. So it simply becomes the CDF at that point in time. Now, to summarize this information, here are 4 events that you are going to often see on failure data or reliability tests. The first row in this column, where we observe the precise time our pump stops working. We observe the failure point, where we might have a sensor which can detect when there is no fluid being pushed through our pump. Well, if we know the time of failure precisely, we simply use the PDF curve to give us the likelihood of observing that particular data point. If we rock up to our pump and we know that it has failed sometime before we rocked up, because we turn up and it's not working, but we don't know when it failed, we use the CDF function to give the likelihood of observing that data point. If we're conducting a test and our pump's still working at the end of the test, well, then the likelihood of observing that evidence, that data, is simply the reliability function evaluated at the end of that test duration. And if we know that our pump failed between Tuesday and Thursday, don't know when, then it's simply the difference of the CDF values evaluated at Tuesday and Thursday. So here are the likelihood functions of each data point that you could possibly see on field data or test data as well. So to summarize a little bit visually, if we have failure data points, if we know when failure occurred precisely, we're interested in the PDF, the bell curve. Could be a bell curve, but the bell curve is an example of the PDF. If we know that our thing failed somewhere before some point in time, then we want to use a CDF function, capital F of T. If we know that our pump is still working at the end of a test, we have to stop the test because we're going to get kicked out of the testing facilities, then we use the reliability function at the end of that test. And if we know that our thing failed between 2 points in time, then we use the difference of our CDF curves values evaluated at those 2 points in time. And for every single data point we have, we simply multiply them together to get, oh, sorry, that's my apologies. That is a summation sign. That should be a sigma sign, a multiplication sign. I'll have to fix that in the handouts. That's an error on my behalf. We actually multiply every single one of these things together. And when we do that, we get the likelihood of all data we observed, which gives us the posse ticket. It gives us the likelihood of our of that particular probability density function or probability distribution getting through into our final posse that allows us to make decision actionable information. But so just to remember, there's an error on this slide. It shouldn't be sigmas, it should be pi's, capital pi's, to signify that we want to multiply every single likelihood of each data point we observe. So the next thing we need to do, and we're going to cover this, yes, there is another webinar, it's going to be perhaps another couple of webinars. The next thing we need to do is use our likelihood function, which we created based on our data, to inform our decision using that magic thing we talked about, using Markov chain Monte Carlo simulation. So before I go on and talk about what we're going to cover next month, are there any questions on what we have covered in today's webinar, or anything you need me to go over in greater detail? Making sure I can see all the questions. Okay, so there's a question. Is the likelihood defined in percentage? Not necessarily. That's a good question. It is a relative probability. So it's actually conceivable for it to be, in some cases, more than 1, because the PDF curve, our bell curve values can be higher than 1. A lot of the times when you have lots of data points and you multiply them all together, it turns out to be a relatively low number. But no, it's not really expressed as a percentage. That's one of the reasons we call it the likelihood, because it can, in a weird way, exceed value of 1. Now, the reason it exceeds a value of 1 because there's a weird mixture of not only probabilities in there, but probability densities, which is a whole new stats class. The point is that if you work out that number, which could be greater than 1, it then drives essentially that posse ticket. It drives the likelihood of that candidate probability distribution being let into our posse. So yes, the likelihood can be greater than 1, which means that we don't often express it as a percentage, because that could mean we see a number which exceeds 100%, which is 9 times out of 10, an alarm bell or a warning sign for any sort of data analysis. We just stick to the number. It's a good question though. Any more questions? So the absolute likelihood value is dependent on the number of data points. Really good question, David. Yes, absolutely. Because each data point has its own likelihood. And so the overall likelihood of that candidate model you're investigating is a product of all the likelihoods of each data point. So obviously, if you get more data points, then it will influence the likelihood of that particular Weibull distribution, for example, because you have to multiply it by one more likelihood function of that new data point you've just observed. So can't we mix the different failure modes, and can that be addressed by the likelihood function? Absolutely, you can mix them. Now, if I sense you're talking about, sorry, before I answer that question, Srivatsan, is when you say different failure modes, are you referring to failures where we either 1, know exactly when they failed, or 2, know that your thing failed in an interval? Is that what you talk about when you're talking about mixing failure modes? So in bearings, it can be pitting or spalling. Okay, so if you're talking about failure per se, I mean, it comes back to decision. Okay, so if your bearing, for example, has failed when it has pitting or spalling, then the event you are interested in to inform whatever decision is the failure event, which includes both pitting and spalling. If the decision you're informing is all about just pitting, then obviously you need to incorporate just pitting failure modes with data points representing the time you observed pitting across some threshold level. So I can't answer that question because I don't know what decision you're trying to inform. If the decision's based on failure and failure includes both spalling or pitting, then you have to include both types of failure modes in your data. Does that make sense? Cool. Any more questions? One thing I will talk about right now, I can see someone, I think it was you, Srivatsan, talked about the maximum likelihood theme in some of the comments today. So I'll quickly elaborate on that in greater detail, just so you guys know what we're talking about. You might recall, okay, here we go. So that question come through. Talked about maximum likelihood estimation. All right. So let's go back to the series of slides. where I showed you this first candidate PDF curve. And I showed you that how conceptually we calculate the likelihood of this PDF curve. And you can see on the scale on the right-hand side that it is roughly 14%, where 100% is the top of our scale. And if we compare that to this, this one here is actually an exponential distribution, it has a likelihood that is so low it barely registers. We're talking about billionths of a percentage point in terms of likelihood, in terms of this scale, sorry. Now, the most likely curve was this one. When we're looking at the field of all possible Weibull distributions, that's important. When we're looking at, it depends which distribution you assume is going to fit the data. So when we're looking at all Weibull distributions, there is computer code out there. In fact, there's actually equations you can use to work out the parameters which define the curve which has the maximum likelihood. So in this case, I set the scale on the right-hand side to be 100%, or at the very, very top, where that has as much likelihood as is possible for all Weibull distributions. So the top of the curve represents the likelihood of the most likely Weibull distribution. Not 100% per se, it is the likelihood of the most likely Weibull distribution. So all maximum likelihood estimation is about finding this curve here, which has the highest likelihood. That's all it is. And when you do that, you get, let's see, you get those parameters there for this particular scenario. So based on these data points, the Weibull distribution, which has the biggest likelihood, is the one which has a beta parameter of 5.0864 and an eta parameter, or characteristic life, of 1.676. So when we look at the next slide, which compared to roughly similar PDF curves, one is actually 7 times more likely. The maximum likelihood estimate is the one that's 7 times more likely. It's very hard to see in a very quantifiable way when we're looking at it with our own eyes. But yes, that shorter one, the fatter one, the one that's a little bit to the right, that is the maximum likelihood estimate, because we did some analysis, we did used some algorithms, used some computer stuff to work out that of all the Weibull distributions, this one has the highest likelihood. Now, that's all maximum likelihood estimation is all about. In fact, I used that maximum likelihood estimation technique to get the line of best fit on the Weibull probability plot. So that line there represents the maximum likelihood estimate based on these data points. So that's all MLE is. So MLE just gives you your best guess. It doesn't give you the posse, because the posse includes a bunch of different distributions, and we want to use this posse to investigate the thing that matters most for our decision maker. Now, our maximum likelihood estimation in this case gives us a warranty failure probability of 8%, but that's all it gives us. Instead, for us to know more about the question or about the decision, we need to understand the uncertainty of our warranty period failure probability. So that's one of the key differences about what we're talking about here. Maximum likelihood estimation is all about a best guess. Does that help answer your question, Srivatsan? Cool. Any more questions? Thank you, Mark. Hopefully that's answered your some of the underlying issues you guys had before we started. So what happens when we have a lower number of failures? Perhaps MLE tends to be biased and gives a positive picture that it actually is. How does MCMC work with lower numbers of failures? Okay, so it's a really good question. I'm going to answer that in greater detail in the subsequent webinars. But to summarize what that would mean right now is what happens if you have less data? It means you have less information. So if we go back to our posse of distributions here, you can see that they're sort of clustered around our 30-odd data points. Now, we use this posse to estimate failure probability at 2 years to give us this histogram over here. Oh, I'll go back one. Histogram over here of failure probabilities at 2 years. Now, if you have fewer data points, what that means is you have more uncertainty. What that means is that you're more likely to have a wider range of viable distributions into your posse, which means that histogram is going to be less certain, which means your histogram is going to be less clustered around a particular point. You'll just have less information. But the good thing about MCMC is it characterizes the information in that histogram. So if you have, let's just say you have half as many data points, but based on the same process, you would expect that this histogram here, which is depicting the failure probability at 2 years, to be much shorter, much fatter, because it has more uncertainty. You're not nearly as certain about what the failure probability will be because you have fewer data points. Conversely, if you have more data points, you'd expect this histogram to get taller and narrower around the true value. So MCMC, there's no threshold about when you can and can't use MCMC. It will characterize the uncertainty, which is what makes it a really useful technique. No matter how many data points you have, it will characterize the uncertainty. Where we start talking about having enough data points is when you are focusing on that line of best fit, which is useless 9 times out of 10. The line of best fit doesn't characterize the uncertainty you have in that line. So the MLE will not necessarily introduce a bias per se. It's just that it's more likely to be wrong. And when you're talking about as few as 4 or 6 failures, absolutely, that will come into play as well. And again, I can explore that in future webinars where we look at this same problem, but have fewer data points, less information, and see what happens in terms of our decision-making profiles. But that's a really good point you raise. There's no lower threshold. It just means your outputs will be less certain, be more spread. And 4 or 6 failures, that's more than okay. When you think about it, that could be enough to inform your decision. Because let's just say your wireless modem router only has 4 or 6 failures, but they're so far to the right of 2 years, they're occurring so far beyond the point that you're interested in. So you have 4 or 6 failures, but maybe in accelerated life testing, it implies a failure at 10, 12, 13, 14 years. That's still might be enough information for you to say, yes, we can launch a product or not. Because while there's more uncertainty, your best guess is actually a long way away from your danger zone. So that's why I always like characterizing the uncertainty of your decision actionable information, because it could just be that you have, sure, not a lot of data points, but it still might be enough to make a good decision. Cool, thank you. We only got 2 more minutes left. Are there any more questions or any more comments or bits of feedback you'd like to throw my way before we call it quits for this webinar? No worries. Again, if you do want to talk offline or outside of the scope of this webinar, you've got my contact details. My contact details are, if you don't, my contact details are on senderreliability.com. And again, we're going to keep going on this journey. Next month's webinar is all about what Markov chain Monte Carlo simulation is. It's not. It sounds scary, but it's not. The reason why I'm taking you through all these concepts is because for you to be able to use this sort of stuff to create that information we showed you in last month's webinar, you really need to understand what each thing does. We're not trying to teach you a textbook definitions of the formulas and equations, at least not yet. But for you to know what the likelihood function means, you need to know this stuff. And when it means something to you, you know how to use it later on. Otherwise, you're just copying numbers from a textbook You're going to make mistakes. You're not going to realize when the assumptions are wrong. You're not going to realize when it doesn't apply to your product. But hopefully now you know what the likelihood function is, which means you now know how to apply it in your scenario. So next week, we're going to talk about what Markov chain Monte Carlo simulation actually is. It's all done on your computer. We're going to illustrate what your computer's doing so you know what Markov chain Monte Carlo simulation is all about, which means you know how to apply it to your situation. And once you know these things, then it's going to be really simple answering all these hitherto complex and challenging reliability problems. No worries. Okay, thanks for the good feedback from Mark and Trivison and Jeff. I know I'm sort of dragging this out a bit, but like I was saying to Fred, I think it's very important for you guys to really have some useful tools to understand, useful illustrations that guide your journey in terms of making these analyses, taking these analyses to the next level. Okay, if that's it, if there's no further questions, it's 1 minute past the hour, we might call it quits there. Thank you all for your participation again, and looking forward to you guys joining me next month. Thank you, Kirk. Thank you, Nana. Annika, thank you.